So weird that you don't use Control V. You don't use the shortcuts for copy paste.
I thought that was a shortcut. You got to teach me some of these things.
You don't learn. In Photoshop. Remember how Photoshop went?
Use the shortcuts for copy paste.
I thought that was a shortcut. Hello, everyone. As you can see, I'm here with, and this is not a photoshopped image here. This is my son, Adrian. As you know, he's part of the show. He was always part of the show, but he went to Argentina, and today I arrived in Argentina to visit my dear son.
Yep.
And so I asked him if he wanted to participate today in the transmission, and he said, yeah. So we're going to do a little bit of broadcasting here, and we're going to be doing time. Let me tell you why I chose time for today. Looks like JFG is going to interview me one more time, fourth time now, and we're going to be on there probably sometime around mid-February. And the subjects that he wishes to discuss, or that we kind of agreed to discuss, are one, the issue of energy, second one, the issue of black holes, and the subject of today, time. And so I'd like to start with that. One way to start is finding out, what do we mean by time? What does everybody mean by time? We always use this word and we don't have really a good idea what time is. We say, well, time is what a clock measures, time is what passes. We use all these words, but we don't really know what we're talking about, do we? And so a good way to start is looking at the definitions of time that you might find out there, and you'll find that these are kind of weird because you'll see they'll say stuff like the first one there from the Wikipedia, and it says time is the indefinite continued progress of existence and events that occur apparently in reversible succession from the past through the present to the future. Oh, okay. Another Science Daily says time is passing nonstop, and we follow it with clocks and calendars. We follow time. Remember that. You follow after that, right? Chase after it. Yet we cannot study it with a microscope or experiment with it, and it still keeps passing. We just cannot say what exactly happens when time passes. And the NIST, National Institute of Standards and Technology, they're the guys who control the time in the United States, out of Colorado there, and they say, according to the NIST, they say it's time is the designation of an instant on a selected time scale. And what is a time scale? An agreed upon system for keeping time. Now, how's that for a circular definition? So, bottom line, we have no idea what time is, and so this kind of raises a question: what the hell are we talking about? No one has ever been able to define time. And as a result of that, Mr. Einstein, he comes up with some weird theories that are very popular today, and some are known as time dilation. You have gravitational dilation. You have kinetic time dilation. You have all these time dilations, and we need to figure out what they're really talking about. What do you think about that? Time, what is time?
Oh man, I think we're just in awe about sequences of events. We're really in awe.
Is that what time is? Just a sequence of events?
No. I think humanity is in awe of the fact that you can have something like a domino effect, where we see that and we're like, what is
one event after another?
Yeah, well, exactly. A series of events. We can't get our head around how, when something ages, for example, it's just a series
Why are you looking at me?
It's just a series of cells doing their thing. It's like a chain reaction that just kind of goes along. And we see that. We see the before and after. We see frame by frame we have memory of each frame of this movie, of this person getting older. and we just say, "Wow, something is affecting this person." Something
But not
is,
time. You cannot
something
say that.
is time is attacking this person. You can
But
say
this
it
is the
like-
point. But
metaphorically speaking,
okay, that's
you could say,
different.
metaphorically you could say time is really.
Poetry is.
I mean, time is taking a toll on you, Pops. It's
yeah,
that kind of
but
thing.
that's
But
poetry.
when you get down to
Physics.
the science, there's no such thing as time because you're just talking about a sequence of events, like a domino effect going down. When
Okay.
you talk about a guy aging, it's just you. If you go really into the nitty gritty, you're really just talking about this cell moved over here, this cell did this
Motion.
exchange.
Is that what it is?
But it's not just motion.
Okay, but what's
yeah,
the difference
it's-
between
it's motion, but I'm saying it's motion in a pattern we can recognize when we see someone age. When we see someone age, and you see it many times, you say, okay, time is an effect. It's a thing happening.
Okay,
something
but,
that happens
but
to
when you
someone.
say that someone aged,
Yeah.
you're saying that you're introducing memory.
Yeah.
Because the
That's
only
what
way
I'm
you
saying.
can figure out that he aged is comparing him against his past,
Yeah.
his past self.
Yeah.
And so I'm saying that that's what the difference between time and motion is. Time incorporates memory. You do not need memory for motion because motion is defined as two locations of an object, right? So we have two locations of the same object. Here it was over here and here it was over there. And you may say, well, that seems like it requires memory because you got to memorize the previous
Well, here's a
location.
good question.
And that's
for
not
that.
true. What we're saying is it occupied a new location.
Well, here's a good question for
Uh-huh.
that. There are people with short-term memory loss who can't remember things. Can they see things move? Can they catch a moving ball? In other words,
I just forgot what you said.
yeah, because can their mind recognize a ball coming towards
Because
their
they
face
have no
and catch it?
memory.
Yeah. But you're not getting me. He can't. He has no memory, so memory is out of the question. But he can still catch a ball because he can recognize motion even without memory.
Okay.
That's the point.
Yeah. In other words, we have motion, but because the guy lacks memory, there's no time. In fact,
So he has no time, but he has no memory, but he has the recognition of motion.
yeah, if someone loses his mind or his memory, it does create a problem for time. That person would have a lot of trouble understanding time, the concept of time, because he would be reborn again every time he comes back into consciousness or whatever.
He's just always conscious.
Yeah, but it's
I don't know
like,
even how that would work.
yeah, it's so weird, isn't it?
Like,
In
it's
fact, I think there's a movie about a guy who loses his
track of.
memory. He kind of
Oh,
reinvents
there's a,
something like that,
a movie called Memento, but that one is like he has memory for a short bit
and
and then he forgets.
Okay.
But it's not like how would it be to have no memory at all? Is that possible? Because then can you even like follow a thought?
You're always living at the same time.
Yeah, it's like you're permanently meditating, for lack of a better word. You're
Okay.
always in the now.
Okay, so for example, you have a watch, and the watch goes forward, but your mind doesn't. Your mind.
Yeah, that's weird.
No, but okay, but so now the guy looks at his watch and he just woke up, from whatever.
He's always waking up.
He's just waking up.
He's always
So
awake.
he looks, and right now it's 10 o'clock, and then he wakes up again. It's 10:05. So he doesn't have a point of comparison against the previous 10 o'clock. He doesn't have that reference.
So weird.
And yeah, I can't even imagine.
It's weird because in reality, that's all there is. There's only the present. And since we invented the past and the present and the future, I mean, the past and the future we invented with our ability to remember and our ability to project, to see where things are going, which, I mean, I think many animals don't have. I mean, very few. We definitely excel in that department. But because
do
of that,
animals have?
I don't know.
You would
but-
think
but
that.
I would think they have
not
some
all
semblance of
not
it.
all animals.
I mean, you can train an animal, so they have some form of learning, and I don't know if that has to do with time, with memory, or knowing what happened before.
I don't think it does.
But that's what I'm saying. Does maybe any form of learning is associated to that general area of the brain that can project into the future? Maybe not as sophisticated as us, where we can imagine different scenarios and stuff, but they can definitely see where things, like if you train a dog not to piss somewhere, or else you'll whack him over the head every time, then he'll be like, okay, I won't piss there, Like maybe he can't consciously project like, okay, this is exactly what's going to happen when I do that, but he can learn what not to do and things to do and things like that.
Well, take a lion. A lion can already foresee, I think, that in
An
a few
antelope
running. Yeah, he can gauge distances and says, that deer, I think I can catch it. Knowing his
Yeah.
own speed and knowing by experience the swiftness of the deer, he knows he's going to be able to catch that or put his claws up on it because he does give it a try. That means he's already looking at the future and saying, I know the future.
I mean,
I can predict.
all animals do that to a certain extent where they kind of know, whatever you call that, like which opportunities to attempt. Like they know, okay,
Right.
this food I can probably go
That's
for.
my point.
You know, I'll go after the baby because he won't move as fast or whatever.
Right.
You know, they kind of know things in advance and that shit. We just took it to the next level where now it's very hard for us to even stay in the present.
Yeah.
Because we're so efficient at looking at the past, looking at the future to make sure we're safe, I'd say, and kind of trying to prepare for what's about to come, that it's very hard for us to even grasp the present. Even when we start talking about the present or when you try to put it into words, it gets really, really meta, really weird. Because you start saying things like, there's no such thing as the past and the future, so it's always now. But the now that just was, or the now that's about to come, or
Yeah, because now is not a single point. Now is an interval between the past and the future.
Yeah, it's
and we
like,
call that now, but now is a long line. You know, it involves several microseconds for sure, if not, seconds themselves. You know, the now has already gone by.
the now is that point in the hourglass where the two glasses meet, and it's not, and the single grains are like our memory, and it just keeps flowing through, and you try to hold on to the now, but it just goes through and goes through.
Let's see if we can illustrate that.
Oh yeah, there you go.
Here we have the hourglass.
Yeah, that point right in the middle.
That's the now.
It never holds
So
on to a grain.
so there is really no
sand.
now. What it is, we have the past and the future there.
No, there is a now, but it's like you can't measure.
No, but I mean that's my point. There is no now. There's only past and future.
No.
Because as soon as you think about it, we're already in the future. And whatever you just said or thought is already in the past.
Another person put it nicely where they said how the past and the future are also happening in the now.
Past and future.
Anytime you're imagining the past, you're doing so now. Anytime you're imagining the future,
well,
you're
imagining,
doing so now.
but it doesn't mean that you actually do whatever you thought about.
I
in
mean,
the future or in the
anything
past.
that could ever happen can only happen in the now. If I'm imagining the future, I'm still doing so now.
Yeah. The only way you can affect things is in now. There is no future or no past. The past is in the memory. The future is also in our heads. We think about the future, have our minds constantly in the future, what we're going to do this Saturday or whatever. But we always live at the cutting edge of time.
I mean, you can scientifically say it's impossible to do something tomorrow.
Have we made too much of a big deal about time?
Yeah, because we measure our life. I mean, it's kind of like the guidepost to do stuff. If you want to meet at Starbucks at 5 p.m.
Yeah.
It's a very useful tool, this grain counting, so we all know, okay, how many grains or seconds away, how many ticks, and in how many ticks will we be at this place? Because if you get those ticks wrong, then you're going to be at a place, and then I'm going to be there tomorrow, or at the wrong time, we're not going to see each other.
Let alone the coordinates.
Oh yeah, coordinates is different. But just talking about time or how long you've been doing something, that's another measure that we use a lot. How long have you been sitting there? Oh, that's why your back hurts. Or how long have you played the piano? Maybe that's why you're so good at it. That kind of thing where we measure. I mean, it might be our favorite measuring tool.
Yeah, and so much have we fallen in love with time that Mr. Einstein in 1905 began really 1908, 1907, 1908, he began with special relativity. And he comes up with an idea which he later incorporates into his general relativity, and that's this twin paradox. And that's that, this weird thing where your twin brother, he goes out on a trip near the speed of light, and when he comes back, he finds you here on Earth to be much older than him. He calculates this through an equation. I'll show that in a minute. But it turns out that he says that his brother, his twin brother, a guy who came out of the womb the same time as he did, more or less, right? Within a few, maybe a minute or two difference, is much older. The guy who stayed on Earth is much older than the guy who traveled. And he could be 50, kind of like
better
that.
food in space.
You know, he could be, he's just as old as much as he could be looks like his grandfather. This guy aged maybe 1 year or whatever, and the other guy, only mathematical proof here, right? Equations. And the other guy, the guy who traveled, stayed young. He only aged maybe a year. And the other guy, the guy who stayed on Earth, he's maybe 50 years older. So we're talking about a big difference. Now, is that science fiction? Is that nice fantasy to discuss? Or are we going to call that science?
They used it in one of the recent big movies, scientific movies, called Interstellar, where I haven't watched it, but it's something like the guy goes into space and he time travels or something like that, and they talk a lot about that stuff. But
well, there's a lot of time travel movies.
Oh yeah, but they don't.
It's a subject that everybody loves. No,
but they don't all involve going out to space at warp speed.
Yeah.
That's what I'm saying. Like it's like a time machine.
Yeah.
You just go into a time machine. It's like they don't really care about the science about it.
The first guy who came up with the first story of time travel is Mark Twain's A Connecticut Yankee in King Arthur's Court.
Yeah, it's a nice one.
And it talks about this guy who is in the 1870s, 1880s. He goes back in time to the days of King Arthur, 5th century AD. And of course, he takes all his knowledge, his understanding of technology of the 19th century, he takes it back. And among the things that he knows is when an eclipse is going to happen. And he knows when it's going to happen, like I think in the year 528. And he tells them in advance, oh, by the way, if you don't let me go, I'm going to blacken the sky. And, and they don't believe him. Suddenly the sky goes black. And so they think he's got superpowers. And yeah, knowledge is power. But it's the first story that talks about time travel. And since that came a lot earlier than Einstein's theory, you can think that there were many people talking about time travel in those days. In fact, The Time Machine by H.G. Wells, also, I think it's 1895, something like that. So all these stories came around that time right before Einstein and some of the other mathematicians, Minkowski and some of those, they started talking about time travel and about considering that as incorporating it into science. What do you think? Is time travel possible? Can we travel through time, in time, towards time, or
even in Hollywood movies? We can't make it make sense.
Why not?
Even in science fiction, the plot just never make sense.
Well, yeah,
no matter what.
Hold it. You go back in time, and you don't want to kill your grandfather. Okay, we'll skip that one. But why can't you go back in time, see Napoleon, shake hands with him?
Because they always talk about things like the butterfly effect, where if for example, if time travel were possible, we'd have a whole bunch of time travelers messing up time. Like that thought just.
Are you saying time travelers from the future that visit us?
Yeah,
today?
We'd have a whole bunch of time machines just popping up out of nowhere, just doing stuff.
But
or our timeline would be changing every 2 seconds.
Maybe I should clarify something which is important, which you should be aware of, and that's that Mr. Brian Greene. We'll address the questions in a second. Give us a second there. Brian Greene, famous mathematical physicist, he's a celebrity, right? And he says you can go forward in time, but you cannot go backward in time. Now, this is what he says, not what he does, because then he comes up with a very interesting scenario, which I'll just illustrate here. He jumps into a wormhole, wormhole is what connects two universes. Black hole is an entrance to a wormhole. You travel through this tunnel, known as a wormhole, and you can travel into the past, according to Brian Greene. Even though he denies that it's possible, he illustrates it. Here he goes, right? He's in the present. He falls into where he was this morning.
I'm pretty sure we had a Patreon about this same
thing. Yeah. That's where I pulled it out. So here he jumps into the wormhole. He ends up seeing himself early that same morning. So he is traveling to the past just by jumping into a wormhole. So now this is now you look at that and you say, oh, okay, that's science fiction.
That's another problem.
That's fantasy. But this guy is saying this is science. What you're staring at there.
That's another problem with time travel movies, with the duplicating yourself one.
What's wrong with that? You see yourself.
Yeah,
but it's not yourself. It's another self.
Yeah, but it gets way weird. Like it just sounds like it would break the universe. Anytime you talk about, like, you can't think about time travel movies too long because at some point you go
crazy.
It doesn't make sense.
Hold it by what's the guy's name? A guy who traveled to the future. What was it called?
Back to the Future.
What was his name? Marty McFly. Marty. He goes back like in the second or third movie. He finally goes back so many times that he finds like 2 or 3 of himself. He finds all these scenarios where he's watching himself
do stuff.
Yeah. So now it gets complicated.
So if even in the movies it doesn't make sense, obvious. Like you think if we can't even if Hollywood can't even make it make sense, there's no way like the laws of nature would make it make sense.
Let's go.
It wouldn't match.
Let's go with some of the. Let's see what people have to say about that. Okay, we have Lazar here. Going back in time is simple. Just move every atom backwards and then replicate yourself. You're saying, okay, that's like what is it in Star Trek, where they go in there and they what is it? They transform you. They translate you into another...
you're talking about the teleportation.
Teleportation. They teleport you. So you're saying teleport you with a teleport machine, one atom at a time.
No. He's saying...
Essentially, that's what he's saying.
Yeah, take every atom that moved let's say you want to go back a day.
Yeah.
Every atom that moved, you record, I guess, the path that every atom took. Let's say you had God's powers, and you basically rewind the tape, and every atom goes in the opposite direction. Okay, but let me tell you what the problem is. I'll illustrate that for you, Lazar. Here it is. Look. Man, some of those would be weird. You see like an egg going back into its shell and then resealing and things like that. It's like playing a movie backwards.
Here it is. Look at this GIF. Let me make it get bigger. Okay, this is God's cabinet, okay? Now, he's got all these slices of time. Each one of these, you can consider them to be a second or a microsecond or a nanosecond. It doesn't matter. Just give it whatever, that cross-section of time there. You think of it as thick as you want. And so God has this file cabinet, and if you want to visit Napoleon, all you have to do is pull out the slice that has 1815 on it, and then I guess if you can move to that slice, well, you have moved into the same time frame as Napoleon. But again, the question is whether you need to move every atom of yourself backwards, or you got to move the Earth. I mean, are we saying that we have to move the Earth backwards until we reach the point where the Earth was in 1815 with respect to the sun with respect to the Milky Way?
He's saying every single atom in the
universe has to move backwards, And so we have a problem with that because that's a lot of effort for God to do. I mean, poor God, he's only got so many superpowers.
In that sense, you can imagine it, but...
Well, can you?
I can imagine
I don't even think you can imagine.
No, you can imagine every atom just going backwards. It's like playing the film of life, just back, and not only life, the universe. The film of universe, just playing it backwards until you get to Napoleon. But like cutting yourself out of the frame, and then when you finally get to Napoleon, pasting yourself.
Yeah, but I'm saying something else. Look, I'm saying it's not only the question of moving every atom in your body.
No, it's
moving.
He said universe.
Oh, okay. Oh, every atom.
Every atom.
Okay, you got to move every atom back. But the point that I'm trying to make is the Earth has to be with respect to the sun in the same way that the sun with respect to the center of the Milky Way and the remaining of the stars, and the Milky Way with respect of all the galaxies in the universe, they have to be in a certain position to find Napoleon there, because that's where Napoleon was, where all these stars and all these planets and all these asteroids and everything was, 100 plus years ago.
Last time we talked about time travel, we talked about a funny thought experiment where if some alien, like light years away, put a very powerful telescope to Earth, he wouldn't see us now because we're so many light years away. He'd see Napoleon and stuff like that. And he's pointing the telescope not where we are, but where the Earth used to be, because light takes so long to get to wherever he is. It was some weird thing like that.
Okay, so are we
see
saying, let's
the
see,
past.
okay, let's see if that's true. We're saying that the image of Napoleon,
It's
right,
it's
is
floating
still flying,
somewhere.
still flying through space, going to some alien civilization that can still pick up that light image
Yeah.
arriving to them. So when they receive it at their telescope, right, they would see Napoleon, not you, because you haven't happened yet.
Well, you have, but the light is still traveling.
Yeah, right. You have happened, but the light has not happened. In other words, has not been
Hasn't gotten
transmitted.
the signal hasn't gotten there yet. He's got low Wi-Fi.
So, Einstein is saying that, yeah, when we look at the night
yeah.
sky, we're looking at the past because
Yeah.
every star that we're looking out there, like, for example, take Andromeda. The Andromeda galaxy as a whole is 2.5 million light years away. That means traveling at the speed of light, right? The light from Andromeda would arrive to Earth in 2.5 million years. That means that when we receive light in our telescope today, we're looking, maybe the Andromeda galaxy doesn't exist anymore.
Yeah.
Maybe we're just receiving the light coming from there.
Yeah, it's weird. Well, last time we talked about sound dilation, the funny one.
Yeah, I got that.
I don't know if you still have it.
Yeah, I've got the equation here, which is the important one, sound dilation. Yeah,
But yeah, not talking about sound dilation.
No, but it's important to understand the equation.
Last time we talked about sound
Yeah.
dilation, it made me realize that everything that you perceive is always the past.
And always through sound, through light.
Through light, sound,
We
or feeling.
evaluate it through
Even
light.
with feeling, it's there's a lag between when you touch it and when you feel it. So
A very small
Same thing with light. Like
It's almost instantaneous.
It's almost instantaneous. But if you think about it, like strictly logically speaking, everything is in the past that you perceive. You're always perceiving a lag.
Yeah,
Which is weird.
and the issue here with these equations is this equation is the one that's used for light. And what we're saying here is let's replace light with sound. Will we have the same situation?
But you got to talk about the context. Like,
Yeah, the context here is that here we have the velocity of the object. Let me make it a little bigger so that...
But what is this the equation of?
This is the equation that Einstein used to make his case for time dilation. And the reason that he could come up with that is that he fixed the velocity of light, which is where you see the word sound there. So think of velocity of the object traveling near the speed of light and the velocity of light, which is just replace the word sound by the word light. And if you put that in there, you do this calculation, what will happen is you will be traveling near the speed of light. What that does is, you have to divide time, the time above, below that number, which is going to be a 1 minus a number smaller than 1. Okay, because the velocity of the object can never be as fast as the velocity of light.
So the closer you get to the speed of light, or if you pass it, you have to shrink time to make up for.
Well, no, time will dilate. It's the other way around. You're going to take the square root of 1 minus a very small number.
Make it longer.
Yeah, and so
a second becomes 2 seconds.
But now, what if we replace the speed of light with the speed of sound? Will we have the same situation? You travel at the velocity of the object, which is, if sound travels at, we'll call it in air, right? 343 meters per second in air. Let's say you travel at 342 meters per second in air. Will time dilate because of that? And let's take it even worse. Let's make it that you travel faster than sound.
They do.
Okay? So now you're right. And so now you travel 345 meters per second in air, right? So now we have a greater velocity of the object than the velocity of sound, which is what we're using as our standard. And that whole equation goes to scrap because now we're going to have time augmentation instead of we're going to have time in the opposite direction.
But I like this way of looking at it because it kind of puts into perspective the fact that we use time but perspective time.
But not only that, we're using light as who selected who said light? Why use light as a standard, as the yardstick?
That's the thing when he said, oh shit, it takes light this long to get here. And if you go faster, then it'll take longer for that light to hit your eyes. Like if I were going, like the sun is to my left, but if I were going to my right at the speed of light, or sorry, just like let's say a little bit under the speed of light, it would take that light way longer to hit me.
Yeah.
So in that sense, it's like it would take me much longer to perceive that light, and that taking longer to perceive it is what Einstein took as time is being bent here, because it takes him way longer. Would take me in that situation way longer to feel light in my eyes.
Let's illustrate that.
And we replaced, basically, instead of light being the measure of how fast, or sorry, how long time is going. I don't even know what the adjective would be. How slow time is going, how fast time is going.
Yeah.
Can you talk about time going? Anyway.
Well, here's an illustration
you could
of that.
just as well use sound. If we're just talking about how long it takes something to be perceived.
There's no you can take the speed of a lion. I mean, why not use that as a standard?
Yeah,
why use the speed of light? Well, what is so magical about light that we would say, look, we're going to relate time to light and the speed of the object? Well, we can just as well relate, any speed in there. Why choose light? Light is an arbitrary criterion, to evaluate time dilation. And here you have an idea of what Einstein had in mind based on what you just said. Let me illustrate that for a second here. And that's, here you have a train passing a station. And you can see these bubbles. Those are what is it? You have lightning hit the front of the train, and it hits it at the same time as the back of the train. It hits it at the same time, but the passenger on the train sees the light from the front of the train first because he's traveling in that direction. So he's traveling towards the front lightning, and he's traveling away from the back lightning. So lightning will take less time to reach him from the front of the train than from the back of the train.
I hope lightning doesn't hit him.
Light is coming to his eyes. But see, the passenger sees, that's the passenger. Now the observer that's on the platform, he sees both of them strike at the same time, because as soon as the train passes, lightning strikes both regions at the same time, and those two lights, he's not moving. Those two pieces of light, just those photons hit his eyes at the same time.
It's weird.
And so he's saying, and so that's where relativity comes in to play. He's saying light or time is relative. It's relative because it depends on the motion of the observer. If you're the guy that's moving and you're moving towards the where the lightning struck first, that light is going to come to your eye first. If, on the other hand, you're standing still like this guy on the platform, both the front and the end will be more realistic, will be just like it happened. In other words, if lightning struck the train at exactly the same time on the front and the back, you're going to see reality there. And the problem is they're making this an observer-related incident.
I really don't like this because it falls apart so quickly. When it's like, who cares what anyone saw?
Right, it's what happened.
I mean, if the observer off the platform were blind, does that mean it didn't happen because he didn't see it? It doesn't make sense.
But it's interesting that Einstein would say that as an argument against Bohr in the 1927 Solvay conference. He said, "I would like to think that the moon is not there. It is still there even when I don't see it or when I close my eyes." Yeah. And this is the situation where Einstein is introducing observers and their opinions. He's saying the guy on the train sees something different than the guy on the platform. Well, who cares? The bottom line is, from a physics point of view, all we care about is, did lightning strike the front and the back at the same time, or did it not? That's the only issue. And the issue is resolved, when we carbonize Einstein, we put him in the hot seat. Here I put him in the hot seat.
You still have that?
Yeah, we have the train passing by there, and we have the situation where if the two lightning bolts going, or the electricity going to the electric chair, if the train hits them at the same time, then we have enough power to fry the guy there. In this case, Einstein turns into this carbonized guy. And if, on the other hand, if the train hits one wire before it hits the other, so that these are two separate incidents, then the guy doesn't get fried. And what do you think would happen? I mean, reality would tell you that this guy gets fried, and Einstein's equation would tell you that it's an observer-related phenomenon, where it depends on what the guy, what his opinion is. And this is the problem. They've
Yeah.
introduced opinions and observers into mathematics by doing this.
But not only mathematics, it's like that seems to be the biggest problem around the topic of time.
Uh-huh.
Objective time versus perceptive time or perceived
Right.
time, assuming that you can divide them like that.
The guy who lost his
Because-
memory we were talking about, I mean, if he perceives time in a different way because he loses
he
his
just
mind,
doesn't.
does that mean that, things didn't happen at the same time because he has a problem with his mind? Of course.
And
Not.
but then you still have to contest with the domino effect thing, where if you touch that first domino, time or whatever you call it, we have this notion that there's time passing as these dominoes push the next one, This chain of event, the fact that we can recognize chain of events,
Mhm.
that is time for us.
Yeah.
At least in the most primitive sense. The fact that we can see this happening and we say, "Oh, I know where this is going." So you saw the future.
You can predict.
Yeah, but it's really just everything just happening in the now. But and that's the objective time, so to speak, the predictable time.
Yeah.
But then when we talk about this, we talk about perceptive time, where we say, how much time do you think passed?
Well, let's find out. Here we have Shamus, and he says, the now has thickness.
Yeah,
The now, which again is an interval, right? Talking about just one now is like talking about a plane without thickness.
yes. But it's weird when
And
you
that's
talk
what I'm
about
saying.
the
There is
now.
no such thing as now.
But it's weird when you talk about now, because some people's nows are pretty long, while other people's nows are pretty short. What I mean by that is some people feel minutes go by like they're hours, and some people feel minutes go by like they're seconds.
Yeah,
If
people
you're-
who are in prison.
For example,
Time is
it's-
dilated
it's-
in prison.
yeah, perceptive time is dilated everywhere.
Yeah,
If you're having fun doing something, time goes by real quick.
Yeah, it's
But
too
if-
short.
But if you got to go to work, those 8 hours turn into 8 days. Weird, huh? Weird how that works.
Okay, someone says there is certainly sequence though, so saying tomorrow is fine. Yep, which tick?
Oh, he's
Yeah.
talking about which tick.
Yeah. But again, we're talking about we got to be careful because with time we have a tendency of jumping back and forth between the scientific treatment of science of time and the ordinary speech or poetry, or as I like it to call it, the poem type of time, where you can talk, figuratively. You can use time in any old way, but you're not talking in a very precise way of something. And the mathematicians would like you to believe that because they can treat time with seconds and minutes and hours and whatever, and put it in the equation, that it's an objective issue. And we get into this situation again with illustrated by the twin paradox, where this guy goes out, comes back, and he's younger than his brother who stayed behind because he was in an inertial frame of reference. And I'm saying that's nonsense, and it's very easy to debunk. Very easy. You say, how many years, how much older is this guy than the other guy? Well, supposedly the guy who stayed on Earth is 40, 50 years older than his twin brother. But this is very easily determined. How many times did the Earth go around the sun? We don't need atomic clocks for this. We just need to know what the definition of the word year is. And the definition of the word year, here we have it. Here you'll see it. This is Einstein's version. And this is my definition of the word year, and that's the one that's still in vogue today. What happened to that?
Or not.
Here, just goes to the bottom if you don't get it right. Okay, so there you have it. Einstein's definition of the year is how many blips the cesium wave has, right? So many blips per second. And the definition of the word year is, how many one revolution of the Earth around the sun. And so the way we figured out the second originally is by chopping up the rotation of the Earth around the sun in, what was it, 38,000, 48,000 pieces. And today they replaced that with the second, and the second is determined by the cesium wave, so many blips. And he's trying to figure out how old one of the two twins are using the atomic clock instead of using what we use today to define the year, which is one revolution of the Earth around the sun.
Yeah, it doesn't matter where the twin went.
Right.
The sun is still.
How many?
I mean,
when the guy came back, how many revolutions of the Earth around the sun? Were there 10 or were there 50?
50 for this guy, 30 for that guy.
Right. And that's the problem. The problem is you can't have that. The Earth went around the sun only so many times, and so you can't use different standards to make to prove your point. You can't use atomic clocks to talk about years. We don't measure years in atomic clocks.
I like what he says
with
about Napoleon.
Okay, so let's continue.
Waiting for Napoleon to reflect from some faraway mirror.
Yeah, okay. Laza says it's not possible, and Shamu says reversing atoms won't reverse time. Because the sequence of moving back and forward again is still after the first trip forward. And and here's another issue, Shamu. Let me see if I can illustrate that as well. Here's the issue. See it here. This is what happens when you go back. If you want to visit Napoleon, you jump into the time tunnel, right? And you go back in time. This is the question. The $1 million question. What happens to your wristwatch? Does it go backwards also?
No.
And this is the issue.
It would strap off your hand,
go
back to where you bought it, and then it would disassemble at the factory, and then all the pieces would go back into the earth.
Aside from that, we have the situation where if you're falling through the time tunnel, your clock is going to go forward, not backward. It's still going to mark time forward because it doesn't know that you're traveling through time. The hands on the clock are physical, and they don't understand that you're traveling through time backwards, unless you tell them somehow, if I'm going to travel back through time, I want you to go backwards. No such thing. The clock will keep going forward. You're going backward. And it's like, like Shamu just said, you're going to take that from the point of view that, any time after the present, which is when I started going into the time tunnel, is future.
It's the future.
So it doesn't matter. It's the future period. It doesn't matter if I go back to see Napoleon. I'm also visiting the future because it's time after the present. So whatever happens after the present, I call the future, and seeing Napoleon in the past is also the future. I just went further in time on my clock, and that clock tells you that I'm going further in time from the present. So yeah, it's all nonsense. Mathematically, it might make sense. Physically, no sense whatsoever.
No, but I like what he says about the mirror.
Okay, so let's
that
go.
Would be cool.
Then Eliza says, I'm waiting for Napoleon to reflect from some faraway mirror.
That'd be pretty cool. If they're like a planet, they're like
a mirror, because
we focused on that mirror, we might see like dinosaurs or something.
That's a good one, Lazar, because what it means is that if we put a mirror wherever, let's call it
really far
at what is it, the Klingon? We'll go to the Klingon planet. That's over there in the other universe, right? Okay, so light from Napoleon goes all the way to the Klingon world, reflects in this mirror. Now it's coming back to us. And that would be funny. What would we see? Would we see good old Nap go into Waterloo and fighting his battle, or
that'd be really trippy?
Yeah, because it's a reflection. Yeah. It should reflect what happened.
Actually, that is a good question. I don't know if it's for this topic, but do signals like that ever die? Like a light signal.
Especially if you have several mirrors and they go bing, 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 just back and forth between mirrors. Then does it ever die? Or it just repeats itself eternally?
I don't think so. I think now that the more I think about it, I think it's actually not true that you can see the past. I think what we see from Andromeda is a very corrupted or very, maybe the signal is nowhere near what it was when it started. Because I think a lot of signals lose their power or get altered when they hit other atoms. So
remember,
we get a very different.
When we see very little Andromeda, we see just a little spiral there, right? And that's because that's the best telescopes we have. Essentially, we're picking up light But the question is, from this faraway entity. But the question is, if light is arriving at the telescope, right? Is that the same thing as the telescope being forward? Like if we could advance the telescope physically and place it much closer between in the distance, exactly halfway between the Earth and Andromeda, what would we see at that point? Would we see Andromeda bigger, or would we see what happened in the past in Andromeda? A closer past.
A less
you see what I'm
distant
saying?
past.
Less distant.
You'd see it bigger and from a less distant past, and it would be clearer. The image would be clearer because there's less corruption. I don't know what to call it.
Look at it with the rope model. With the rope model, it does make sense. You say, okay, we reflect Napoleon against the mirror, and the mirror in this faraway star now sends it back to us 100 years later, 200 years later. So now we receive the image from Napoleon in the year 1815. We receive it in 2015, right? Okay, 200 years later. So that light went out there 100 years. Now it came back 100 years. It's back to us, right? What happens if we put a mirror now? So we have this mirror and it goes back and forth, right? Back and forth eternally, because we have this mirror shining the same light back and forth, going from one mirror to another.
Would it bounce back and forth until a mirror goes down?
But now, let's look at it under the rope model. Let's assume that Napoleon, right? His atoms sent signals along each rope that connects him to every atom in Andromeda or the Klingon world, whatever, wherever the mirror is. So his reflection goes, or his light goes out, hits this mirror, in other words, through the ropes. Now these atoms are relaying that same signal back to us, to our mirror, okay? So we have this back and forth, but along ropes. We have the signals along ropes. And the question now becomes whether you can do that through time, or does it matter whether we have time or not? Is it just a physical issue? For example, we have the laser ranging experiment performed from the Earth to the Moon up to recently. I think the Russians are still running it, their own version of it. Essentially, they put a mirror on the Moon, okay? And the Moon is a little over a light second away from the Earth. That means light takes about 1 second plus, let's just round it off to 1 second. It takes 1 second to go to the Moon. So we shine our laser against this the mirror. We'll call it a mirror. That's what it is. Essentially, it's the lunar ranging experiment to find out if the Moon is getting closer or farther away. That's why they did this experiment. So now we shine our laser. It's pointed to this mirror. The mirror reflects it back to us, and we collect that reflection, and we say, look, the Moon is so far away, or now it's closer to us, now it's farther away. That's what they did this experiment for. But imagine now you put a mirror here on Earth, and now so you have the light going to the mirror on the Moon, now coming back to your mirror and going back and forth as many times as it wants. You see the issue? All they have to do is put a mirror here, and we'll find out if light loses its energy as it hits one mirror and comes back and then goes back and forth. Or what we have is ropes interconnected from one mirror to the other, and you send the signal through one rope, and then the reflection comes from one atom there to a rope to an atom over here through the rope that's reflecting the signal. It sounds more logical to think that you can do this much better with ropes, and not to add to discrete particles called photons that can get lost, because we would never be able to catch a reflection if all these photons just if you have curved space in between, they're just curved out of our field of view. That's what would happen. We would lose all these photons. In fact, today we do catch the reflection from the lunar ranging experiment.
Well, light it has to lose its signal, or else if you put two mirrors facing each other, it would just get super bright because the light that bounces between them wouldn't die. You keep adding more and more light, and it would just wouldn't die and wouldn't die. You just keep collecting more and more light. It would just be like a huge sun.
And
of light.
the reason
That's
for
why
that
I-
is very simple. When you relay the signal, you do not relay it with the same frequency exactly
Yeah.
as when you received it. And that's what's happening when when you have an angle, refractive angle, when you send light, say through glass or whatever, you see that light takes an angle. Takes that angle because light is not traveling. Light travels at the same speed. It doesn't travel at the same frequency or wavelength through that new angle.
Or
That's what
angle.
changes. Okay, let's see what else we have here. Reversing atom wouldn't reverse time because...
you read that.
Oh, okay, that one. The next one is... Shamu here says... yet wouldn't you measure... Oh, I lost them.
Oh man, it went fast.
Wouldn't you
We're
measure...
going too slow.
We're going slow today. Yeah, wouldn't you measure the speed of light as the same speed even while you're traveling away from the source at nearly the speed of light?
Yeah, he's saying when I'm going to the right and the light comes in from the left.
Remember, the
speed
speed
still goes the same.
light always has the same speed. What changes is frequency for wavelength. If we keep that, we're okay. If we go with an artificial refractive index where we change the speed of light, then we're crazy.
A lion won't seem to be moving the same speed as we move away or towards the source.
Right, and that's the point. Why choose light as a standard to measure time? That's the issue. The issue is to measure time, okay?
Yeah, Shamu was right about that. If a now with zero duration is as sensible as a plane with no thickness, there's no such thing as a single frame of the universal movie. And yeah, that's what I've said all the time.
Yeah.
You could conceptually break it down to frames to try to explain things, but in the end, reality doesn't have frames.
Except that you can look at it in a different way. You've got the movie of the universe, okay? Here's the movie, and it's already been done. Just the part that's been done, not the future. Now you can look at any of those frames and call any of them arbitrarily and say, this is the now. So you can look at the frame where Napoleon is and say, oh, this is now, 1815. And you say, well, but now has already gone by. We're in a different now. And still, this is
a different now.
Yes.
That already shows that you're not now. One of these is not the now.
Yeah, but see, now is an arbitrary.
Now.
That's my point. My point is now is arbitrary. Okay.
Now this is interesting. One revolution of the Earth around the sun is not a sufficient definition of year because the sun itself rotates.
And I'm sure the Earth doesn't arrive at the same exact location where it left, especially if the whole thing is moving around the center of the Milky Way.
And it's like these things are always in. We kind of get the vague. Kind of, more or less. I mean, we even have daylight savings time.
By the
Things like that
way,
to match.
it's important to note something else. In that equation I showed a minute ago, it's got little c. And one of my objections against all of general relativity, especially when it's applied like to Mercury's perihelion, is that they use little c as a constant. And they say, well, little c is a constant out there in space. In a vacuum? No. The answer is no. Why is it no? Because general relativity holds that every atom produces a gravity well. It curves space around it. Any mass does so. And so if every mass curves space around and the little photon falls into every depression it finds, light would never at all travel space straight. It would travel always in curves.
Yeah, it'd just be like
And if it
snaking
travels,
everywhere.
and if it travels in curves, just one curve, not all it needs to travel one curve. You have angular momentum. Angular momentum means that you lose speed. Just talk to any mathematician, tell them, what is angular momentum? Well, it means that you're not traveling a straight line. Therefore, when you're traveling a curve, you're slowing down.
And you really thought this through, didn't you?
This means that little c should never in general relativity be a constant. It always has to be a variable.
Well, yeah, but you
And they treat it as a constant.
because you got to get the average. You got to get in the ballpark.
Yeah, but they don't do that. They just take the maximum value. Because if you take the average, you would say, well, what's the speed of light through glass? Well, you got to divide it by 1.45, and let's round it off to 1.5, and you get 200,000 kilometers per second. That means light travels through glass at 200,000 kilometers per second. If I take the average, that means light travels at 250,000 kilometers per second. You know, I can't do that. And they don't do that. They don't do that in mathematics. They always take 300,000, and they should not be able to do that in general relativity, because general relativity is full of potholes. And a poor photon falls in every one of them, never travels straight. Angular momentum shows that, or, dictates that you must have a slowing down of the little c. And so little c should never be little c. The other one, just to keep in mind, related, is that the gravitational constant g used by general relativity is measured using the Cavendish spring experiment, the torsion balance. And when you use the torsion balance, that's done here on Earth. You can't do that because the gravitational constant g is a earthly determined variable constant, but out there in the macro world of planets and stars and galaxies, you cannot use this constant. It's not determined for a macro scenario. The gravitational constant g just is determined here on Earth. It should be used only in, for example, should be used in quantum mechanics, not in general relativity. General relativity is a macrocosmic theory of gravitation. If you want to use something that you determine here in your little lab, you got to use it only for quantum mechanics.
For all the sticklers you're doing, because really being a stickler, but that's kind of how science should be done. And you'd think, being scientists, they would have been more
careful or
more meticulous about these details.
They're not concerned about qualitative aspects. That's
we're already ending the thing.
Okay,
I wanted to ask, do you have any summaries or any final thoughts on time?
Well, time obviously is a subject for much more than one presentation or one transmission. All I can say about time is, first, the word time has never been defined. It's still an undefined term. That alone
it's been defined, but not scientifically.
Which means it's not defined, for the purposes of physics. That means it should not be used as a word as anything related to science. If they want to use it in mathematics, which is also outside of the realm of science and of the realm of physics, fine. They can do all the calculations they want. That's used for descriptions. When we want an explanation, they can't bring the word time back in there, because we have no use for seconds or minutes. We might have use for qualitative time, before and after. But again, for that, they would have to define the word time, and they've never done so. So the word time does not belong in science or in physics. That's the first issue.
That's weird. That's already hard to wrap your head around.
Yeah, the other issue is that, the word time, the way Einstein uses it, because of all his calculations, he talks about time dilation, about stretching time, and so on. He essentially is treating time as a physical object. That's he's saying that time are these little particles that hit you and make you old.
Yeah, like I told you at the beginning of the podcast. Time is attacking this poor man.
All these particles, these chronons, as they're known, the chronons are hitting me.
No, you gotta lay off the chronons, bro. That's hitting those chronons a little too hard.
It's what's making my hair go white. It's all these chronons.
Yeah, those chronons.
So, to use time in that way, saying time dilation and time does this and time does that, and even talking about chronons, that's where it becomes very scary. That's when you know that, they're misusing the term time just to get their theories across.
Is it accurate to say time doesn't exist, or there's no such thing as time?
For that, we got to go not to the word time, we got to go to the word exist. Exist in physics.
Or according to
the argument is that it can only be used in the context of objects. Time is a concept, so you cannot say time exists or time doesn't exist. All concepts
don't exist.
There's not a single one that exists. Only objects may be said to exist. So time cannot be said to exist in a scientific context. In ordinary speech, we can say, oh, time exists or love exists. We can say that there. In science, we cannot say information exists, time exists, or love exists. We can't say that. Or energy exists, or any of those.
Yeah, but it's weird when you try to say time
Yeah, they
doesn't
say-
exist. 'Cause
Yeah,
they say,
because-
okay, then what are we doing? Are we just all crazy? You know?
Yeah, but then that's why people accuse me of doing semantics.
Yeah,
But the issue,
I accuse you too. Let's add one more to the list.
but the issue is, it's not semantics. You need to get the rules of
Yeah.
engagement.
No, I like putting it in the
Right.
context of programming in like a programming language, because if you program something for the computer to understand, you have to put it in. I mean, to call it rigorous or meticulous is an understatement. You have to put it in perfect terms so that the computer understands what you say. And the problem is when
Yeah.
you try to be perfectly logical. Like I've had this problem with
The
you
com-
sometimes.
yeah, the computer
where you're
isn't
so
lying.
logical sometimes, where it's just like I notice at some point, like I'll be using a metaphor at least to explain something in my mind, and all this time I didn't even know it was a metaphor, or I'll
The
just
world
kind of
is
get
flat.
vague. Yeah, I'll just get in the ballpark, but you're like, no, put it precise on. I want to know exactly what you're saying in
Yeah.
perfect language, and it's really
And it's not.
that's that. I
it's
told
not
my dad
harping
that's
on-
that's the hardest part of physics.
Yeah.
You have to be literal.
Yeah.
You have to be perfectly literal and
Yeah.
perfectly logical, and it just gets really hard because we're just so accustomed to speaking in vague terms and metaphors and poetry
in tongues.
in tongues. Yeah, it's kind of like
Okay,
you
let's
know
see.
what I mean.
Let's see if we can get a. Okay, see, you're right. Reversing atoms would not move back light in time. Yeah, for Laza. And Samu says it's really a trip back to an imaginary point on a revolution in relation to where the face of the sun was pointing last year. Yeah, yeah. Again, it's playing around with time creates so many paradoxes that it's not even worth considering. What these people do is they say, well, this is what the calculation says. This is our physical interpretation, and we'll never understand Mother Nature's universe. So don't try to understand what we're saying. Just try to understand our description of it,
Yeah, it's
mathematical.
such a bummer when they say we can't understand the universe, or
Yeah.
I don't know. It's so defeatist. It's like, really, you think the universe works in such a way that we can't wrap our heads around it?
No, and there's something more. Like I'm saying, you can say, well, how do those rockets go into space? Well, I don't know all that technology. But look, you have two little magnets. One attracts the other. That's the entire system. And to say that no one today at any university on the planet, at any think tank on the planet, can tell you how this piece of metal attracts that one or repulses it, that's where you kind of take a step back and say, well, hold it. No one can explain this.
No, the weirder one for me is gravity. The fact that
More or
no one
less the same.
explains- Yes,
Same thing,
But
yeah.
that was weird because you don't deal with magnets every day, but
Okay,
gravity
you drop
is-
the pen, you let go of the pen,
Gravity
then falls to the
permeates our
floor.
life just completely, and
What's the
it's,
system?
It's so real that we just take it for granted. So, yeah, gravity.
Yeah,
But when you try to
yeah,
explain how
yeah.
it works, people just say, "What do you mean how it works? It just is."
Right, and the
It's
issue
like,
is, the only way to
okay.
find out how it works is by identifying the invisible mediator. Because if you don't do that, you're in essence introducing spirits in that same space. And with that, I'll see you next time, hopefully on Sunday if I'm still in Buenos Aires. Okay, so we'll see you then. Okay, bye-bye.